This lecture is part 2 of Section 3.3 from Math 311, the course in linear algebra at Western Illinois University. We are going to finish the section on invertible matrices. And let me just remind you what an invertible matrix is, right? We know that, so remember that if A is an n by n matrix, we said that A was invertible if and only if A times B is equal to the identity matrix, which is equal to B times A, for some matrix B. Okay, and we showed that the inverse was in fact unique, so we denote B as A to the minus 1, A inverse. Okay. And what we sketched out the process of finding an inverse. If an inverse exists, we showed how it goes. Basically, it was this process where we put our matrix A and the identity matrix right next to each other. So we have a matrix with n rows and 2 n columns, and then we use elementary row operations to transform this, the left half of this matrix into the identity matrix, and then whatever is over here was the inverse of A. And that's if A is invertible. Of course, not all matrices are invertible. We talked about that. Now, we kind of said we didn't exactly show why this always works. We showed that if there is, find a way that if we can do this, if the inverse A is invertible, then whatever's over here has to be the inverse. But we wanted to prove something a little bit more. In fact, we're going to be proving quite a bit in this lecture today. But we're going to show that a matrix being invertible, there's a lot of stuff that implies, not just this. So, going to the notes today, for today. So again, this was the definition of the of invertible matrices, and we said that if A is invertible, first of all, that implies that the matrix equation AX equals B has a unique solution for every column vector V, right? Because we can, if A inverse exists, we can just apply A inverse on both sides, and we get that that X is going to be A inverse B. Okay, so this holds for any column vector B, and of course we're assuming all the dimensions agree with each other so that this expression makes sense. A special case of this is when B is 0. Then in that case the AX equals 0 has only one as the unique solution, and that has to be the trivial solution given by X equals 0. And then from there, we learned that when we were solving homogeneous systems, we could do this. We can write A, the coefficient matrix A, on one side, and the 0 vector on the other, and we could do elementary row operations and get that. If there's only one trivial solution, we would get this. Well, what that means is the reduced row echelon form of A would have to be the identity matrix. And when you think about this, if you have an n by n, the reduced row echelon form is going to be a square matrix. It's going to have n columns. Okay. Now, if all of those columns are pivot columns, then the only way that the only possible reduced row echelon form where you have n pivot columns is the identity matrix. However, if you take if you don't have n pivot columns, if you have, let's say, n minus 1 or fewer columns, then you're going to have a row of zeros. And when that happens, that means you will have you're going to have free variables, and you'll have more than one solution to this equation. So it's, that is, if it'll tell you if the reduced row echelon form is something like 1 0 3 0 1 2 0 0 0. Okay, if that's the reduced row echelon form of A, and then if you were trying to solve the corresponding system represented by this augmented matrix, and if your variables were x, y, and z, we know that this would mean that x plus 3z equals 0, and y plus 2z equals 0. So you get that x equals negative 3z, y would be minus 2z, and z would be z, and you'd have infinitely many solutions. And then that would contradict this statement, right? So that's why if A is invertible, its reduced row echelon form has to be the identity matrix. Okay, which strongly suggests that when we should be able to compute the inverse just by doing this process of reduced row echelon form in what we were doing here. That it should always work. Okay, so we're going to show that these four properties are actually, well, we show that this implies this, and then implies this, and then this implies this. We're actually going to show that these are all equivalent. In fact, we're going to prove something more than that in this lecture today. Before we do that, though, we need to talk about elementary matrices. And first, what's an elementary matrix? It's a matrix that can be obtained from the identity matrix by performing exactly one elementary row operation. So here, in particular, an elementary matrix has to be square. Okay, and we start with the identity matrix. We perform exactly one operation. Here, this is an elementary matrix because we've just taken the identity matrix and we've just added 2 times the second row to the first row, right? This corresponds to the elementary row operation 2R2 plus R1. Here, what we've done is we've taken the 3 by 3 identity matrix and multiplied the second row by 3. So this would just be 3R2. That would be that operation. And here we can see that we've taken the 3 by 3 identity matrix and we've interchanged the second and third rows. So this would be R2 interchanged R3. So you want to think of an elementary matrix as just a way way of describing a single elementary row operation. You're just performing it on the identity matrix. Now, one of the nice things about these is these can the effect of doing an elementary row operation on a given matrix corresponds to just multiplying that matrix by the corresponding elementary matrix on the left. So, in particular, if we take this matrix up here and we multiply this on the right by the matrix A, B, C, D, if we do the calculations, we get this matrix A plus 2C, B plus 2D, CD. So basically, we've done just performed the same operation on this matrix. We've multiplied this row, the second row, by 2, and we've added to the first row, which is what we get how we get here. If we take an arbitrary 3 by 3 matrix and multiply it by this elementary matrix on the left, we do the calculations, we see that has the effect of multiplying the second row by 3. And if we take this third elementary row operation, elementary matrix, multiply it by this arbitrary 3 by 3 matrix, we can see that this has the effect of interchanging rows 2 and 3, just like we did over here. Okay, so that's why so multiplying an elementary matrix on the left corresponds to just performing that operation on the original matrix. We also will see that these matrices are invertible. And that just goes back to the knowing that the elementary row operations are in fact invertible. The inverse of 1, 2, 0, 1 is 1, negative 2, 0, 1. The inverse of this matrix is just 1, 0, 0, 1, 0, 0, 1 third 0, and 0, 0, 1. You can check all of this. And we're going to see that in this case, this matrix is its own inverse. And this kind of makes sense because, if you switch two rows and then switch them back, you get exactly what you started with, right? If you take a row, multiply it by 3, and then you multiply it by 1/3, you're back where you began. And if you add twice a row to another row, and then add negative 2 to that same row to the second row, you'll get what you started with. So you notice that these inverses are actually elementary as well, right? This is an elementary matrix that corresponds to negative 2r2 plus r1, and this corresponds to the elementary row operation 1/3 r2. This corresponds to r2 interchange r3. Okay. All right. So to summarize what we've just been discussing, looking at these examples, we have a few facts that we've more or less discovered. So fact 1 says that if E is an elementary matrix and A is a matrix of the same size, then EA is obtained from A by the same row operation that E is obtained from I. That might seem like a mouthful, but if you understand the examples on the previous sheet, this is just what we're talking about. So this thing right here, this expression, IN with RI interchanged RI, this thing in parentheses represents the elementary matrix that corresponds to this operation. Okay. So if we multiply this by A, we get A with the ith row and jth row interchanged. If we take the matrix, which is IN with the alpha times the ith multiplied by the ith row, multiply it by A, we get A with the same operation where the ith row is multiplied by alpha. And if we take this matrix where it's the identity with alpha, alpha times the ith row added to the jth row, multiply it by A, we get A with alpha times the ith row added to the jth row. Okay. All right. Then we also see that they're invertible, and that these matrices are invertible. In particular, if we had at the elementary matrix corresponding to this operation where alpha Ri replaces Ri, then it's going to be this matrix, where the identity with 1 over alpha times Ri replaces Ri. Okay. All right. So the elementary matrices are invertible. The matrices right here, these are just diagonal matrices where everything except one entry is equal to 1. And then these matrices are they're ones on the diagonal with one other entry which is not 0, which is alpha. Okay. All right. So if you buy this, the most important fact here is that invertible matrices are in fact products of elementary matrices. So how is that happening? Well, if we start with a matrix A, okay, and if we apply the first operation, row operation, we get E1 times A. And then we apply another row operation that has the effect of multiplying this by E2 on the left. Okay, where E2 is the operation the matrix corresponding to the second operation. and then we have E3 and so on, and then, you know, eventually we get EK minus 1, and let's say EK. Okay. So let's say if we do all this, and if A is invertible, then we should get the identity matrix, right? All right. And then we, so this just reflects that you know, that the IN is the reduced row echelon form of A. Okay, so in particular, the reduced row echelon form will also always be, you know, a series of elementary row operations times A. And then what we can do is because they're invertible, we can first multiply both sides by EK inverse. Okay, so we get then we get EK minus 1 through E2, E1, A is equal to EK inverse times IN, and then multiplied on the left on both sides by the inverse of EK minus 1, so this will be EK minus 2, E2, E1, A equals EK minus 1 inverse EK inverse IN. And we can keep on doing this until we get that A is equal to E1 inverse, E2 inverse, EK minus 1 inverse, EK inverse times IN. Okay, and then this in fact is going to be that we'll get that, and of course IN just acts as the identity, so this in fact is going to be E1 inverse, E2 inverse, EK minus 1 inverse, EK inverse. Okay, and because the inverses of elementary matrices are elementary matrices as well, this will be a product of elementary matrices. Okay. All right. So maybe just to maybe just skip ahead to page 5 here and just show you how this went. Let's say when we wanted to find the inverse of the matrix 1, 2, 3, 4, we did the following operations, right? We first set A and I here, and then we wanted to get rid of this 3, so we had minus 3R2 plus R1. And we know that that corresponds to the matrix 1, 0, negative 3, 1. Okay. So in fact we have this times let's see, times 1, 2, 4, and that turns out to be this one, this 1/2. And then the next thing what we did here is we wanted to get rid of make this 2 a positive 1, so we multiplied the second row by negative 1/2, and that corresponded to the matrix 1, 0, 0, negative 1/2. Okay, so okay, and that was this matrix. And then finally we wanted to get rid of this 2, so we multiplied negative 2 R2 plus R1. Oh my god, I think this should be the other way around. This was negative 3 R1 plus R2. Yeah, but this does work. Okay, and then this was negative 2 R2 plus R1. So the matrix that corresponds to that would be 1, negative 2, 0, 1. Okay, and that in fact is the equal to the identity matrix. Okay, and then so this was A, this was E1, this was E2, this is E3, and this is the identity. And so A is going to be E1 inverse, E2 inverse, E3 inverse, which the inverse of E1 is going to be 1, 0, 3, 1. The inverse of E2 is 1, 0, 0, negative 2. And the inverse of E3 was 1, positive 2, 0, 1. Okay. And again, what we're doing is we found these inverses just by taking the inverse of the elementary row operations that they represented. Okay, so this is A, and if you multiply this out, this in fact is equal to 1, 2, 3, 4. Okay. If you don't believe me, just multiply this out. Now, will you have to do this on a test? Probably not. Okay, on homework maybe once. But the important thing is that that you get the principle that every matrix, every invertible matrix is a product of elementary matrices, because every invertible matrix can be reduced to the identity by a series of elementary row operations. That's all what we're saying here. Okay, so if we go back to page 4, we have the first version of a very, very important theorem, probably the most important theorem in linear algebra. That's the fundamental theorem of invertible matrices. And we call this version 1 because by the time we're all said and done, there's going to be about 15 things that are listed here. So what the theorem says is the following. If A is an n by n matrix, the following are equivalent. That means if any one of these statements is true, then all of them are true. Okay, and either of the statements. A is invertible. AX equals B has a unique solution for each column vector B. AX equals 0 has only the trivial solution. A is a product of elementary matrices, and the reduced row echelon form of A is the identity matrix. When I was writing this, I wrote 4 and 5 out of order, but I didn't want to rewrite everything. So the way we're going to prove this is we're going to show that 1 implies 2, 2 implies 3, 3 implies 5, 5 implies 4, and then 4 implies 1. And that means everything implies everything else. Okay, so here's the sketch of the proof. For 1 implies 2, we covered that at the beginning of the lecture, right? If A inverse exists, we can take, and we're given AX equals B, then that means we can multiply on the on the left by A inverse, and that gives us that X is A inverse B. Okay, so that's the only solution. 2 implies 3. Well, 3 is a special case of 2. We just use 2 with B equals 0. Okay, and there's a unique solution, and that's a trivial solution. To show that 3 implies 5, we also did that because it has to be the reduced row echelon form has to be the identity, because if anything else, if it's not, you get free variables, and that means you get more than one solution to AX equals 0. So if the RREF is not equal to the identity, then we have at least one free variable. and infinitely many solutions to AX equals 0. Okay, next, we have 5 implies 4. Okay. So that just refers to the fact that if the reduced row echelon form is the identity matrix, that means that there are going to be, we can write, we have elementary row operations, or elementary matrices ek minus 1, dot, 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 through E2, E1 times A is the identity matrix. All right. So for A, and then this, we showed from there that A is in fact the E1 inverse, E2 inverse, through EK inverse. Okay. So we proved that. And then we see that the A is invertible because we can see what the inverse is. The product, well, actually we can just take the inverse of both sides because the product of invertible matrices is going to be invertible. Remember, if we remember the formula that the inverse of AB is B inverse A inverse, right? Then we can see that this, we can generalize this a little bit and see that the that A inverse is going to be EK, or rather, let's see, yeah, E1, sorry, EK, yeah, it could be EK minus 1, E2, E1. Okay. And yes, that is, that's correct. Because if we, yeah, so that's going to be the inverse. We can multiply, if we multiply this and this together, this times this, we can see the EK's cancel. If we multiply this times this, first the E1's cancel and everything else. So you can see that, so that means that A is invertible. Okay, so that tells us that 5 implies 1. So or I should say 4 implies 1, sorry. Okay. And that completes the cycle. Okay. So that means, so all of these are equivalent to each other. And we're going to see that there's a lot of other stuff that we'll be adding to this. Okay. So, that's all we have for today, and we'll see you next time.